Okay, so as I just mentioned, we'll be looking at hidden surface removal today. So I'm going to start off by just explaining why we need this next step. Eight. Okay, so this is the graphics rendering pipeline, seen it many times. If we just have a look where we're up to, so the previous work we've done this term is all about projection onto a viewing plane and then clipping to the unit cube. Okay, so that means you get the clip screen space. So we're at the clip screen space, everything, we've removed any polygons which are outside of the viewing area. We've clipped polygons to the edges of the viewing area. So all we've got now is polygons which are seen by the viewer. But things in a real world, things aren't transparent. You can't see what's on the other side of that wall. And so these are what we want to do next: is remove things, remove any surfaces that can't be or shouldn't be seen by the viewer. Okay, so what do I mean by that? Okay, so that's our village. Okay, so this is our virtual world. We've done everything. We've transformed all of our objects into the world space. We've aligned the world space to the viewing position. We projected it using perspective projection. We've now clipped it. Okay, so the blue rectangle, that's my edges of my unit cube. So if you have a look at the x-axis, it goes from -1 to 1, and same in the y-axis. Okay, but as you can see, it still have a wireframe appearance. So I mean, this house, which is closest to the viewer, we can see through this house to, for example, the church behind. Obviously, we shouldn't be able to do that. Okay, so that's what we want to be doing with hidden surfaces. Determine which surfaces should be seen, which shouldn't. Okay, the particular technique we're going to be looking at today is particularly useful for when we've got enclosed objects. Okay, so this is an object called the Utah teapot. It's quite a famous object in graphics. On the left, what I've done is I've drawn it using all the polygons, and I've made polygons transparent so you can see through it and you can see to the back. Okay, so you can see it's kind of like a wireframe 3D object. The one on the right, what I've done is exactly the same polygons. I just haven't drawn any polygons which we shouldn't be able to see if we're looking at it from where you're looking at it from right now. So it's exactly the same polygons. Okay, these are transparent polygons. So these ones here are transparent. So they're like that. But the difference between these two is this one doesn't have any polygons which I shouldn't be able to see. Okay, so our challenge is we have to somehow tell the computer which polygons we shouldn't be able to see and which ones we should. Okay, so that's what we're going to be looking at today. Just sort of by the by, really, just going to mention about this teapot. Okay, this you may sort of see this quite often, and the reason why it's kind of a famous object is Martin Newell, who was way back in the late 60s, early 70s. He was developing a lot of these techniques that we're doing today. Okay, and he needed some object which was three-dimensional, multiply connected, and he needed some object to use to test all of his methods. And so his wife suggested, why don't you use this teapot? Okay, so what he did is he sort of drew the teapot on some graph paper, worked out all the 3D points, and he used that. And so it's become a bit of an in-joke in computer graphics. Everyone uses it. And so, as you can see in Toy Story, if you've ever seen Toy Story when Buzz Lightyear is having tea, you know the bit in Toy Story where he goes next to, have you seen Toy Story? Oh, I've got to see Toy Story. Yeah, so the bit where Buzz Lightyear gets sort of used by the girl next door, and you know, there's a teapot, and it's even appeared in The Simpsons. Have you ever seen this episode? Simpsons, yeah, there's a teapot in the background there. So it's kind of like an in-joke. It's actually somewhere in all the Pixar films is this teapot, as they like to do in jokes and things like that. Okay, so that's By the way, that's nothing to do with what we're going to, you won't be testing on that. It's just a little bit of an amusement. Okay, so what we're going to be doing is having a look at various methods. Okay, so a lot of these methods are used together with each other in conjunction or instead of. So kind of like all these methods are depending on what situation you have. You use these. The ones we'll be covering is backface culling, which is this morning, and that's used in assignment 8. It's actually a very, very simple method, very dead easy. It won't take me more than about 20 minutes to actually explain that. Painter's algorithm, again, very straightforward. We'll cover that on early next week. That's assignment 8 additional tasks. So the basic assignment 8, use backface culling. If you want to sort of increase your mark a bit, we can use painters. Newell's algorithm, the Z buffer, and assignment 9 will be on something called binary space partitioning. This assignment, when we get to there, is nothing to do with MATLAB. So if you don't like MATLAB, you'll probably like that assignment. And that's all sort of a hand calculation. That's a very this binary space partition is a very neat, clever method. Okay, so that's what we're going to be doing over the next couple of weeks. Okay, quite a few of these well, in particular backface culling, but a few of these hidden surface removal methods require the normal vector for each polygon. I've mentioned this, and Killian's also mentioned this a number of times in the past. Normal vector points perpendicularly away from the polygon or from the plane, and we use the cross product. So between any two vectors, so if this is vector A on our polygon, and this is vector B, also on our polygon, if we find the cross product to them, we can calculate the normal vector. We usually use a convention, but as we're looking at the front face of a polygon, by front face, I mean the face which the normal vector is pointing away from. So this, if I was to look at this polygon down in from on top, that's the front face. If I was looking at it from underneath, I'd be looking at the back face. Okay, and we use anti-clockwise order. So if I take my A vector to be the vertex 2 minus vertex 1, cross product with the B vector, vertex 3 minus vertex 2, that will give me that normal vector. You've seen that a number of times in the past. I'll probably also repeat it in the future, just to cover it. Okay, backface culling. The hint, clue is in the title, backfacing. What we need to know is, given a position in which we're viewing our virtual world, what polygons are front-facing and what polygons are back-facing. So this is our viewing position. I tried to draw a little eye here. This polygon here is front-facing to the viewing position because we're looking at the face of the polygon which the normal vector is pointing away from. So the polygon on the top is front-facing to this viewing position. I called it P here. The polygon on the bottom is back-facing because we're looking at the back of the polygon, which the normal vector is pointing away from where we're looking at it. So we're going to be dealing with front and back-facing polygons in hidden surface removal. And the backface culling method essentially removes any polygons which are back-facing. As simple as that. So, okay, well, before I talk about that, because polygons only face in one direction, if you're creating a virtual world, and let's say that wall over there, we use a polygon to represent that wall, okay, and the normal vector will be pointing towards us. Well, if you're the other side, you'd want another polygon with the normal vector pointing away. So when we build our virtual worlds, if you do have walls, you normally need 2 polygons. So for this wall here, even though it's a single wall, we need 2 polygons, one facing one way, one facing the other way. When we look at binary space partitioning, we require our polygons of our virtual world to be pointing in to the room. So if we have this room here, the polygons which would represent all the walls would be pointing inwards towards the room. If you have an enclosed object, like the teapot, or here we got the house, Okay, the polygons need to point away from the center of that object. Okay, so that's this is taken into account when we design a virtual world way back in the object space and the world space stage. Okay, so the method of backface culling, as the title sort of hints at, is we remove any surfaces that are pointing away, i.e. backfacing to the viewer. So here we've got a hexagonal object made up of 6 polygons A through to F. And this object is viewed from this position over here. Okay, polygons A, B, and C are front facing. That means if I was to draw a line between the viewing position and the center of the polygons, it falls on the front face of each of those polygons. Okay, this V is what viewing vector really. So the viewing vector is the vector that points from the viewpoint P towards the center of the polygon. Okay, so for example, this V, center of the polygon A, that's that vector. Polygons D, E, and F are back facing. Okay, so as we're looking at them, we're looking at the back face of D, E, and F. Now, if I was just to remove D, E, and F entirely from this object, we'd only see A, B, and C. But as looking at it from position P, we wouldn't know that we can't see D, E, and F because they're being obscured. So essentially, that's what backfacing culling does. It just cuts off the back of any object we're looking at. Okay, so how do we know? We can easily see by visual inspection whether we're looking at the front of something or the back of something. Of course, as I keep mentioning, computers don't have eyes. Computers only understand numbers. So we're going to have to find a way in which to determine whether something's front or back facing. Okay, so here we've got those same 2 polygons. We know that the polygon A at the top is front facing, polygon B at the bottom is back facing. Okay, and I've put on their normal vectors and their centers. Okay, so if we look at polygon A, I've drawn the vector V, which is a vector going from the viewing position, i.e. the eye, through the center of that polygon. Okay, so now I've got 2 vectors. I've got N and I've got V. And if I look at the angle between N and V, I'm going to call it theta, we can see that angle is greater than 90 degrees. It's greater than pi over 2. Okay, so that front-facing polygon, the angle between the normal vector and the viewing vector is greater than 90 degrees, i.e. pi over 2 in radians. If we look at the bottom polygon, we do the same thing again. There's my viewing vector. We look at that angle, again, theta. We can see that's less than 90 degrees. So that's going to be less than pi over 2. Okay, so what we do is we calculate, or we can calculate the angle theta. If it's greater than pi over 2, it's front facing. If it's less than pi over 2, it's back facing. Unfortunately, calculating an angle requires sines, cosines, tangents, expensive calculations. What we can do is simplify it using the dot product. Okay, so if you recall, the dot product of any 2 vectors is the magnitude of those 2 vectors multiplied by each other, multiplied by the cosine of the angle between them. We need this cosine of the angle. We need to know what the angle is. Or do we? Because the cosine of theta, if it's less than, if the angle is less than 90 degrees, cosine is positive. Because it starts when the angle is 0, cosine is 1. When it gets to pi over 2, it's 0. So when the angle is between 90 and 180 degrees, the cosine is negative. So that means instead of actually calculating the angle and calculating the cosine, we just say, well, is it positive, is it negative? So cos theta is negative if we've got a front-facing polygon. Okay, this is front-facing, so this angle is greater than 90, so the cosine of that angle will be negative. If the cosine of the angle is negative, remember these 2 are both positive numbers. I'm not going to calculate them. I don't know what they are, but they're both positive numbers. So two positives multiplied by a negative gives me a negative. So therefore, if I calculate the dot product between V and N, if that's negative, we've got front facing. If it's positive, we've got back facing. Dot product's dead easy. Calculate a dot product, multiply the elements together, add them up, boom, you've got the dot product. Very, very simple, easy calculation. So this is the algorithm. Again, I've presented this in quite a formal way, just to get you used to how we do it. Okay, so back-face culling method, what we need is we need vertex coordinates of polygons, and we need a viewpoint P. Okay, so in programming sense, vertex coordinates will be like a vertex array, and polygons link this will be poly. And we have coordinates of your single viewpoint P. Okay, quite often that will be, if we transform the screen space, P will be a coordinate with a Z value of less than -1. Doesn't matter what it is, it's the X coordinate will be usually 0, Y coordinate will usually be 0, Z coordinate will be somewhere. It doesn't matter. Doesn't matter what the Z coordinate is because we're only looking at the dot product. Okay, so for all polygons in our world, well, after clipping and what have you, calculate the normal vector for the current polygon, calculate the center of the current polygon, therefore we can calculate the viewing vector, which is just C minus P. So once we've got V and N, calculate the dot product. If it's negative, we render the Okay, so it's as simple as that. We only bother from here on in, we only bother with polygons which V dot N is negative. If V dot N is positive from here on in the viewing pipeline, we just totally ignore it. Okay, and that's what you get if you apply it to the Utah teapot. What I've done here is on the left, I've rendered all polygons, and I've made them opaque, just so if I was to sort of twist that, if I was to rotate that teapot around, I'll do it in a future lecture. Using MATLAB, you can see I've rendered every polygon. And then this one on the right, I've assumed, let's say the viewing position is around about where the cursor is here. And you can see that anything on the back side of the teapot is totally ignored. Only the front-facing polygons are rendered. Now, if I was to look at it from this point, I wouldn't know that these back-facing polygons aren't there. Okay, but it doesn't matter, you know. And essentially with back-face culling is normally you reduce the number of polygons by half. So we're removing any unnecessary polygons, and we're reducing the amount of computation from here on in by half. Okay, if I was to do that to my village, okay, I'm just going to go right to the. Okay, so that was at the beginning. That was after I've clipped. Okay, I've clipped to the screen. That's what we have. And if I apply back-face culling now, okay, something's not quite right. Okay, this sort of house which was right at the front, okay, that should have been front and center. That should have been obscuring anything which was behind it. Now, as you can see, this church, or what I've sort of tried to draw a church, is now slapped there. So back-face culling, it has reduced the number of polygons in our space by half, but it hasn't quite given us a good image. That's where we're going to use Painter's algorithm. So the algorithm we're going to be looking at next week, early next week, is on Monday. I'm looking at another method called Painter's method, which will sort that out. Okay, essentially that is back-face culling. Anything about what I've just mentioned? Anything you're not quite sure on? Any questions you have? Okay. Do you think you'll be able to draw this teapot? You define all those coordinates. So that's what your assignment 8 is. But I'll give you the coordinates. Right, okay. So I'm just going to quickly mention assignment A. You looked at me like really, you know, oh my God, he's not going to make us do that, is he? If I go to the Moodle area for this site, for this course. All right, what are we on? Graphics. This is a part where I hope I have actually uploaded. Oh, there we go. I say, right, I have to upload these. What I will upload is assignment. I will give you teapot coordinates. So what I will do is I'll give you a file of which contains all of the coordinates in the vert and poly type lists. So you'll have a vert array, which will contain all the vertices. You'll have a poly linked list array, exactly the same way as we've been working with so far. So you don't have to do these. You can actually, I'll give you these coordinates. If you want, you can download them online. If you do a Google search for the Utah teapot, the data set is available. But your assignment 8 is essentially draw the teapot, loop through all of the polygons which construct the teapot, calculate their normal vector, do the dot product between the view and vector, and the normal vector. If it's positive, plot it. If it's not, don't. Simple as that. So that's what your assignment 8 will be about. Right. What I want to do now is